So I received some email that some of you have like class during my office hour time. So I can do individual Zoom meeting or so my time is very flexible on Tuesday and Thursday. So if you have time conflicts with my office hour, you can always email me and we can schedule a one-to-one meeting. On Monday, Wednesday, Friday, well, Monday I can only do after 6 p.m. and Wednesday, Friday I can only do after 5 p.m. But my time is very flexible on Tuesday, Thursday, Saturday, Sunday. So if you have any question that you have time conflict with my regular office hour, email me and I can make it work. And let's continue with our content in last class. Oh, by the way, I checked the recording of last class. I think there are like 35 minutes. There was no audio. Because microphone problem. So there's nothing really guaranteed because I don't control the whole thing. The only way that is just take good lecture note and try to focus during these 50 minutes. That recording just back up, but sometimes things happens. So we talk about this was the example problem we didn't finish. We talk about that we have a system with 3 bars, and there's temperature change in the element 1. And the 2 and 3, there's no temperature change. And of course, to simplify this question and only focus on temperature change, we didn't apply any external applied force. If there was any external applied force, should we go into this term, right? Now there's no external applied force, so this term becomes 0. Well, actually, it's not 0. I can talk about it in detail later, but everything related to after assembly, the global matrix equation, that term becomes 0. For the node 4 becomes 0. Node 1, 2, 3, they are reaction force. So because this example is only focused on temperature change, so only temperature change here, no temperature change for element 2 and element 3. And we talk about that to avoid mistakes for this kind of problem. The best way is that you always start with a connectivity table. So you know which is your definition of first node and second node of each bar. And then you know what is the positive local x direction of your each element. And you know what's corresponding phi and corresponding L and M. You can define this node order in any way you want. That's fine. And I mean, you and your friend, you can define in different way, but as long as your solution process they are correct and you keep consistent with this definition, everything should be fine. The final result should be the same. But you just want to make this very clear at the beginning, and it's easy for our TA to grade the exam because we want to know if it's really calculation error or is understanding error. Calculation error, we minimize penalty. Understanding error, you should expect some larger penalty. So this is my definition, and this is corresponding phi, and the cosine and the sine. And for element 1, we talked about in the last class that well, standard procedure, you can always write 4 by 4 for element 1, 4 by 4 for element 2, 4 by 4 for element 3, and then do the assembly. Since we have some students ask me after class like why it becomes 8 by 8. So because now we have after assembly we have 4 nodes. Each node has 2 degree freedom. Moving X, moving Y, right? Each node 2 degree freedom. So the total, the dimension of the K matrix after assembly before we apply boundary condition should be 8 by 8. So the standard procedure is you write 4 by 4 for element 1, 4 by 4 for element 2, 4 by 4 for element 3, 8 by 8 for the entire system, and then you apply boundary condition, everything related to node 1, node 2, node 3, they're gone. Because 1, 2, 3, they cannot move in X, they cannot move in Y. We did all the corresponding rows and columns. So in the end, we have 2 by 2. So now if I'm clear about the whole process, we should understand that everything related to node 1, 2, 3 is not useful information for solving the displacement at node 4. It will delete it in the end anyway. So a method that saves you some time and not wasting time on using this information is that you only write 2 by 2 for each element and do assembly. After assembly is 2 by 2, right? So we had this 2 by 2 for element 1. And there was a question in the last class. The rest part, they are not zero. It's corresponding to this part. And you just plug in the corresponding LM for element 1. Right, it's just not useful, so we didn't write, but it doesn't represent it's zero. It's not zero. So for element 2, since we define the connectivity is from node 4 to node 2, so the row index I can write as U4, V4, U2, V2. Sorry. Right. And of course, if you prefer to define it from node 2 to node 4, that's perfectly fine. And then this row index becomes U2, V2, U4, V4. That's what I mean. You need to always make it consistent in the whole solution. And also to make it easier, I can also write the calling index here. U4, V4, U2, V2. And again, we don't need to write the whole 16 components. We only need the 4. What are the 4 components? What are the 4 components? Okay, so what are the numbers? One over 4. So is this based on what are the L and M did you use? This is yeah. So basically, this is for element 2, right? So we need to use the corresponding L and M for element 2. Yeah. Yes. So because let's say our L equal to 0, M equal to 1. So it's basically, it should be these 4 components, right? So since L is 0, we have zero, M equal to 1. And all the rest component we don't need. Any question on that side? And for element 3, very similar. So now we have A, E over L. Let's first put the row index and column index here. Since it's, well, our definition is from node 4 to node 3. So I should write as U4, V4, U3, V3. Same thing. U4, V4, U3, V3. And again, we only need 4 components, and this equation stay the same. So we now just need to plug in L equal to, so this is corresponding L and M for element 3, right? We just plug in these 2 numbers. And again, it should be these 4 components. So it becomes all positive. Yes, all positive. Any question here? Okay, now we have the K for all three elements. We can do assembly. And of course, assembly, you can just write only 2 by 2. There's no need to, well, let's make it less confusing since it's the first time we do this. Let's say assembly. I can still put this one as 8 by 8. So for all degree freedom, U1, V1, U2, V2, U3, V3, U4, V4. It should be a 8 by 8 matrix, and the common coefficient here is AE of L, of course. And right side we have F1x, F1y, F2x, F2y, F3x, 3y, 4x, 4y. And we have the thermal term. Temperature change is only for the element 1. So this is a AE alpha delta T. Let's put a common coefficient here. AE alpha delta T. And we have -1/2. Let's just let's put it here. Paste. So it's basically -1/2. 2, 3, 4. So the global matrix equation, before we apply boundary condition, the big matrix equation before we apply boundary condition is 8 by 8. But we know that, again, we only need this one, this one, this one. Makes sense or not? All the rest components, it's 64 components. We only need the 4. If you try to write the whole matrix during the exam, I don't know. Don't complain that you don't have enough time for finish the exam. So now we have the 4 components is right here. 1/2, 0, 0. So basically you need to, let's try to rotate this one so you can see the whole thing. We have this one plus this one plus this one equal to 1/2, right? Yes. Yeah. So second component, right? 0. Third component, 0. The last component, this one plus this one plus this one. Make sense? Yeah. So now let's solve for U4, V4. Any question?
For element equation, you also do U3 is V3 and then U4 V4 for that matrix, or it doesn't?
Sorry, what did you mean?
So for element 2 and element 3, why did you put V4 and V4 before V3?
Okay, great question. that's why students keep making mistake in the exams. Again, that's what I keep emphasizing, that you need to make it consistent in your solution. When you define from 1 to 4, it always should be 1, 1, 4, 4. When you define from 4 to 2, it should always be 4, 4, 2, 2. If you define your way as from 2 to 4, then you should always write it as U2, V2, U4, V4. Then in the end, you will get the same solution with your friends who define in a different way, right? So this is a key point, like why I keep emphasizing always make it consistent. You can really define in any way you want. As I said, as structural engineer, if you want to figure out your structure fail or not, it does not depend on coordinate system you define. It does not depend on like which node the first node, which one second node. It will fail, no matter how you define the coordinate system, right? But it just in your calculation process, make it consistent. Any other question? Thank you for the question. Yeah. Okay, so let's do the calculation. We have 2 by 2 matrix equation. We have 2 unknowns. I can write the final answer here directly. So U4 equal to L alpha delta T, and V4 equal to 5 alpha delta TL. Yes. So we are done with the first step, calculating the unknown degree freedom. The second step is calculate element force. How to calculate element force? How to calculate element force for all 3 elements? Anyone? Check lecture notes. Check lecture notes. So this was the equation Dr. provided last week. And I expanded in this way because, I mean, in your solution, when we solve this equation, it's always everything in the global coordinates, right? It's not really in the local coordinates. So that's why I expanded in this way. Basically, you have uj, vj, ui, vi, and you plug in here, and you get everything. And of course, in our example problem, there are some element with temperature change, some element without temperature change. So with temperature change, you have this term. Without temperature change, delta T equal to 0. We're done. So it's basically put our solved U4, V4 into the equation for each element. And just be careful that it's always second node, first node. Again, why I keep emphasizing make it consistent, because the definition of your first node to second node is different with other people. So let's do it one by one. For element 1, P element 1, element force of element 1, we have AE over L. Second node, based on definition, is the node 4. So we have the L U4 and V4 minus everything related to node 1, right? LU1 minus MV1, but U1 V1 equal to 0. So this term is gone, right? Yes, you're correct. So it should be UJ minus UI. Yes. Thank you. So there might be some like notation different in the textbook. Sometimes they put the first node at node I, second node at node J, and sometimes we use first node as node 1, second node node 2. Yeah, you're correct. So the second term is 0. And don't forget the temperature change term, because temperature change in element 1 is not 0. Let's plug in all the numbers. So we have A E over L. 1/2 L alpha delta T. And M equal to negative. And our V4 equal to, let's write this one clear. This is 5. Alpha delta TL. And our temperature term, A E alpha delta T. And its final answer, negative 0.2 A E alpha delta T. So this is for element 1. Element 2, very similar. Since now we are defining our node order is from node 4 to node 2. So node 2 is the second node, node 4 the first node. And everything related to node 2 that's 0. So now it becomes AE over L minus, it's 0 minus L U4 M V4. There's no temperature change, so that term is 0. So we have AE over L. For the L and M, L equal to 0, so we only have the M term, MV4. So we have M equal to 1. Yes, M equal to 1. And there are negative sign here and negative sign here, it becomes positive. Five alpha delta T L. A E alpha delta T. Right. So it should be there should be 0 here. It basically represents L U2 plus M U2, but because U2 V2, sorry, U2 and V2, they are 0. So this is 0 term minus this is the first node of our element 2, and the temperature change term is 0 because delta T is 0 for element 2. The third one, again, we define from node 3 to node 4. So the node 3 becomes the first node. Sorry, I think it's node 4 to node 3. Node 4 to node 3. So first node, second node, right? A E over L. And again, it's 0 minus L U4 plus M V4. And L and M for the third element is different. The equation is the same as second element. So we have 1/2 L alpha delta T. And V4 negative L alpha delta T. So we have negative 0.2 A E alpha delta T. Again, element 3, there's no temperature change. Any question?
I think negative again for like the minus LU4 but LU2.
is 0 minus. So let's go back to the original equation. I think is for element 2 is L U2 plus M V2, which is 0 minus this one, right? For element 3 is L U3 plus M V3 minus this one. Yeah. Any other question? Let me check the example Kim did the last class. So, oh, he did the calculation of the stress. So for calculating stress in tension compression, this is the equation, right? So we already calculate element force for all 3 elements. If we want to know the stress in the structure, divide by cross-section area, because this is simple tension compression situation. It's sigma equal to P element force or internal force from mechanical materials divided by cross-section area, and it's constant at every point in your bar. So you can do that after class. Actually, since he didn't talk about the reaction force in his example here, let's expand this example problem a little bit. How to calculate the reaction force at node 1, 2, 3. This at a third step, reaction force at node 1, node 2, node 3. Lecture 8. This is a lecture note he gave me. So which one? Oh, yeah. Okay. Yeah. Okay. This one has the reaction force. But this is 1D situation. Oh, no, 2D. 2D. Okay. It's everything at node 1. Well, let's say this is a standard method. I can teach you an easier method today. So yeah, this is the standard procedure. Yes. So for this example, he did calculate the reaction force. So let's say for this one, for the example problem today, how to calculate reaction force at node 1, 2, 3. Let's say if you want to use the same method as he talked about in last week, how do we calculate reaction force at node 1, 2, 3? Plug back. Yes. Thank you. So basically, R1x, R1y, R2x, R2y, R3x, R3y. Make sense? Because by definition, external this column should be the external applied force at node 1 in x direction, node 1 in y direction, 2x, 2y, everything, right? And I mentioned at the beginning of the semester that externally applied force at node 1, 2, 3 is the same definition as reaction force at node 1, 2, 3, because you can simply consider it as external applied force at node 1 is the force applied by this pin joint to node 1. It's the same thing. I can use my hand to grab it to make sure it does not move. You can say that, okay, the force applied by my hand is external applied force. But you can also say that it's reaction force, right? So yes, that is a standard procedure. So basically, you need to put these 2 columns of the, you do not need to put all the 8 by 8 matrix here, because again, 0, 0, 0, 0, 0, 0. Right? So basically, the first 6 column doesn't matter, because anything multiplied by 0, we don't care. So you need to write the complete 2 columns here in our 8 by 8 matrix and times. So basically, let's write in this way. this one times this one. Oh, sorry. This one times U4, this one times V4 becomes F1x. Make sense? So you do the calculation, you can have our reaction force, node 1x, node 1y, node 2x, node 2y, node 3x, node 3y, right? Sorry, I cannot hear you very well. Yeah.
Alpha delta T, there's only
Where?
four numbers.
Oh,
Can you
okay.
explain that?
Oh, okay, great. I got a question. Thank you. So y is only here, here, and here, and here, because there's no temperature change in element 2 and element 3. So for this one, for the first one, I wrote a complete matrix equation, right? So I have this term. So this is a node 1, node 1, node 4, node 4. I didn't write the complete equation for element 2 and element 3 because let's say if I have this part and we have for element 2 should be 4x, 4y, 2x, 2y, right? And then now this term becomes 0. Makes sense or not? Because there's no temperature change in element 2. And the same thing, if I write the complete equation for element 3, then it should be 4, 4, 3, 3. And again, this term is 0. And because there's no temperature change in element 2 and element 3. Element 1. Yeah, so that's our problem statement. Only temperature change in element 1, 0 temperature change in 2 and 3. Yeah. Any other question? So I just talked about the standard procedure of solving this reaction force. It's basically plugged back in, and you need to write the complete these two columns of the components, and you get the reaction force at each node in the x and y direction. That is the same method as Dotkin did here. R1x, R1y. It's also put it back. Oh, there's some delay here. This yeah, put it back to the big matrix equation. But let's say forget about math. We actually have an easy way if you truly understand the relation between the reaction force and element force, because element force we already calculated here, right? And if you remember at the very beginning of the semester, when we talk about 1D bar, well, if you take each element out, it becomes 1D bar. And we talk about that there's a relation between the element force and the reaction force. So let's say if I want to generate tension, I define this is a positive, this is positive x direction, so this is node I, this is node J. And to generate this tension, I need to apply force at node I in this direction. And I need to apply at node J in the positive x direction, and node I is negative x direction. And we have positive internal force in our element. And I said, okay, everything in our solid mechanics is in equilibrium. So the magnitude of node I, force at node I, magnitude of force at node J, and internal force, they're always the same because everything in equilibrium. And in terms of sign, the element force is always the same sign as the second node, right? So if I want to generate tension, node J, I need to be goes in the positive x. So positive internal force, positive at node J, but at node I is negative because point towards the negative x direction. And if I want to generate compression, again, magnitude is always the same. The internal force in our element, force at applied node I and force applied node J. So now I apply a compressive force. So node I goes into the positive x direction, node J goes into the negative x direction. So for the sign, again, negative internal force, negative force at node J. So the sign is always the same as the force applied node J. So if we understand this part, actually we don't need to do any extra calculation. Just by understanding that force, internal force of an element is always equal to the force applied at node J. And here, let's say for the element 1, since we define from 1, 2, 4. This is node I, this is node J. So we can say that the nodal force is always equal to the nodal force applied node 4 and opposite sign at node 1. So the reaction force I can simply write as equal to negative P1. Is this clear or not? Because node 1 is our first node. Element force is always opposite of the nodal force at node I. So now we already have the P1 calculated. So now this becomes 0.2 AE alpha delta T. Can save you some time. And what does this one means? So again, this is the number. Of course, you use the standard procedure. You calculate R1x, you calculate R1y, and then you have R1 equal to square root of R1x squared plus R1y squared. You get the same answer, right? You get the same answer. But what this positive number means? So this positive number means that, okay, our definition of positive x direction is from node 1 to node 4. So this is the positive x direction, positive x local x direction, right? And our reaction force is positive, means it's in this direction, which makes sense because let's forget about FEA, forget about all the calculation, everything. You just imagine that this one has a temperature change, temperature increase. Let's consider delta T is a positive value. This one has temperature increase, it want to expand. But now because, well, there's no temperature change in these two, there's a boundary condition here. If the free expansion and compared to with all these constraints, this node and this node should apply some contraction force. Make sense or not? Because that's a difference of, let's say, if you remove this boundary condition, if you remove this connecting with two elements, it becomes the free expansion. Now I have this pin joint. Now it's connecting with two members. That's no temperature change. It means that there's some contraction force applied to element 1. So that's why our reaction force calculated at node 1 is in the positive local x direction. Makes sense, right? So this is also double check like if your calculation is correct or not. And similarly, reaction force at node 2. Now, since our node 2 is the second node of our element, so it's equal to element force directly. Same magnitude, same sign. So P2 equal to right. So, and of course, you can double check. So because let's say our local x definition based on our node order is from 4 to 2. So this is a positive x. Definition node 4 to node 2. And we get a positive value for the reaction force. It basically means that the force applied by node 2 to the element 2 is in this direction, which again makes sense because we already solved that this node 4 will move somewhere here, right? So there is a elongation. There is an elongation in element 2. Or you can understand in the way that, okay, this one want to expand. Even though it's not a free expansion, but still it want to expand. So it will cause the elongation in element 2. And how to generate this elongation in element 2, the force applied by node 2 to the element should go in this direction. The force applied by node 4 to the element 2 should go in this direction. This is how we generate the expansion. Make sense or not? So again, our calculation makes sense. And similarly for element 3, again, element 3, we define that is from node 4 to node 3. Again, second node is node 3. So the reaction force or nodal force and second node should always same sign, same magnitude as element force. Again, we can write directly. R3 equal to P3 should be equal to negative 0.2 AE alpha delta T. And we're done. And in the exam, you can use this method. But again, if you want to use this method, you need to make it very clear at the beginning that this collectivity table. So when TA grade, they know what the positive and negative sign means. Because let's say it may happen that you and your friend have different sign for this value, but both of you should be correct because your definition of a local x direction, they are different. So yeah, even though like in the end, it represents the same direction, but the positive and negative sign may be different because your local x direction definition is different, right? So this is I consider the easy way to find a reaction force. And of course, you can always double check by calculating, let's say you have the complete components here. You calculate 1x, 1y, and then you combine this 1 square root of f1x squared plus f1y squared and compare with the R1 we calculate here. Similarly, you calculate 2x, 2y, 3x, 3y, compare with our calculation here and to see if they match. You can do it after class. Any question?
Was there a cheat pass relative?
I think so.
Okay.
Where is the attendance sheet? So we probably start from next class like 1, 2, 3, 4. So always make sure that don't keep the attendance sheet by yourself. You need to pass on to the people next to you. Otherwise, any other question? I got some question about the exam 1 before the class. So how to prepare for exam 1? So basically, you need to make sure that you understand all the basic concept in our class. All the lecture recording are posted. You need to able to solve all the example problem we did in class. It's not like checking the solution I gave you and see, oh, I understand this is so easy. No, when you actually solve by yourself, you want to expose all those mistakes before the exam rather than expose like get stuck in the exam. Okay, why I didn't figure this one out before the exam? So try to solve all those problems by yourself, and of course all the homework problem. Because I was in the conference last week, I didn't really like assign homework in that week. So this homework is due Friday. But I do want you guys to have some practice of this one before the exam. So I will assign another homework. It's due before our exam review class. Exam review is on Monday. So I will make it a bonus homework since we don't have, I didn't give you guys enough time. So if you really have time, solve it by yourself. It's 1 point bonus in your final grade. Yeah, but I still highly recommend you guys to do it. You need to practice for your exam anyway. Yeah.
Explain the internal forces, like why the signs are specifically like one.
Let me show you. It's at the beginning of semester. Do you remember this part? So
Yeah.
this is how we derive the nodal force at node J and node I. And we talk about to generate tension, the internal force is positive. And to generate this tension, what we need to do is that we need to
But how do you know it's tension? Like, did it say in the problem that
I mean, back to the basics, the theory part. For this spring element, if you want to generate tension, do you agree with that? You need to apply force in this way
yes,
to generate tension. So when it's tension from mechanics material, we know that internal force should be positive. This is a sign convention,
yes,
right? And to generate the tension, we need to apply a positive force and node J, and the negative X direction force and node I.
Yes.
So negative, positive. Makes sense or not? Node I is always negative X direction. Node J is always a positive X direction. This is how we generate tension.
Oh, where did we like find that in the where did we find that in that problem?
This is the first lecture.
Yeah, no, I mean like where like where did we find that the forces were negative in the I direction and positive
So
in
this
the
is a
J
nodal
direction
force, right?
for
Nodal
this
force
problem?
for this problem
Yeah,
is the same thing. It's the same thing. It's the same thing. Let's move back here. This one, the element force is calculated here in the previous step. Right? Oh, this is the element 3. Makes sense or not? We calculate this element force first, and then we calculate reaction force. Is that what the question?
Yeah.
I just don't know how we know it's going to be in tension or in compression.
Let
because
me
we can change the nodes, right?
explain. Let me explain. Tension, compression, no matter how you define node, tension is tension, compression, compression. I define this node 1, this node 2. When it's tension, it's still tension. I define this node 2, this node 1. When tension is still tension.
Oh, so even if we flip the nodes, it'll like still
Again, a bar is in tension compression doesn't depend on how you define your coordinate system. How do you define your first node, second node? When it's tension, it's always tension, no matter how I define it. You define you and your friend can define it completely different way, but it's still tension.
Okay.
Makes sense or not?
Yes.
Yeah.
Right. So sorry. I have no idea what a displacement field is.
So it basically tells you, so in the 1D bar situation, the displacement, the stress is always constant in each section.
Yeah.
When stress is constant, strain is also constant. And we know that strain is the first derivative of displacement. So you know that since strain and stress are constant, displacement should be linear change. And now since you calculate all the nodal displacement, so let's say 0, 0, something, something. You have 4 points, you use straight line. It becomes a displacement field.
Okay.
Makes sense or not?
Makes sense. I just
Yeah,
Never-
because
it-
FEA is really calculating the nodal displacement.
Yeah.
Let's say U1 0, U2 something, U4 yeah.
I have no idea what that like
Yeah,
graph
it
means.
just plot. So you have 4 numbers. You use straight line to collect all those 4 points.
Okay.
And then down.
length versus displacement, basically.
Yes, yes. So x-axis is this dimension, and y-axis is the displacement, and you calculate node U2, U3, U1, U4, that's 0, use straight line to connect those and become displacement field. So it basically means that any point in the structure, I know what is displacement. Right.
Okay.
Yeah.
Thank you.
You're welcome.
I learned this the difficult way in mechanics material exam 1. But yeah, you have to do that you have to make sections according to each of the applied forces on the
Sorry, what did you say?
that you have to section it out according to the forces and the different areas.
Yes,
Yeah.
Yes,
so that's
yes, yes. But that is for stress. This is just only ask you for the
Yeah,
displacement
for the
field. Yeah,
displacement.
yeah,
Yeah,
yeah.
and that's what I did here.
Yeah.
Displacement here too.
Yeah.
Yeah, and lastly for me, you're available after 4-5 today for office hours?
So if I take.
I have class from 4 to 6.
Oh yeah, after 6 is fine too.
After 6,
Yeah.
yes.
Yeah, that's good.
It's still.
I was just wondering,
The same.
so I did like the element matrix for this.
Yes.
You know, to try to keep it that
And
same. way.
when I'm putting it together in the global, I was wondering which of the rows and columns have to, okay, so I see 2 and 3 are boundary conditions.
Yes, everything related to 2 and 3, that's 0.
Oh,
So,
Did it all the rows and columns corresponding to 2 and 3?
here basically.
Yeah.
Oh, all of this. Okay.
Yeah, you only have 2x2 left. You only have the U1, V1,
Mhm.
4 components left.
Okay, yeah, so you're just left.
Yeah.
This.
Yeah, yeah.
G1.
Yeah.
And then I just continue from there. Okay,
Yeah,
Thank you so
yeah.
much. I've just, I made another sentence. It's somewhere. Thank you.
Oh, okay.
Never.
Yeah, where is the, yeah,
And you have officers?
Yes. yes, at 7th in the MAEC 106.
Okay.
Yeah, in the DML building. Yeah.
Could we look at the bottom of the note? I was curious. How is the intuition work for knowing if it's a positive or negative of the internal?
So
force?
it's always, if it's, since this is the first node of an element, you
Yeah.
add a negative sign. If the second node,
Oh, I see. It has to do with how we define the
yes,
convention.
yes, yes, yes. So because in our in my definition, this is the second node, this is the first node, because now it's at first node, I add negative sign.
Okay.
But for second element and third element, these are second node.
Oh, so that's
So
to do with the
positive.
minus the first.
Yes.
Okay. Yes.
Yes.
Okay. Thank
Yeah.
you.
You're welcome.
That, like the reaction forces, the final thing, are there always like, those are local direction? Like the points are local forces or?
This number, they are based on the local code, your definition. But in the end, you and your friend should, even they have different number, they should be represent same direction.
Correct.
Yeah, same direction. Yes.
Okay. And
Yes.
so on the exam, it doesn't matter the sign.
On the exam, you need to make sure that you make this clear, so we know what is the positive and negative means.
Okay.
Right.
Okay, thank
Yeah.
you. And then for the displacement field, I wasn't
Yeah.
sure if I did it correctly, but is this like, so like you have displacement at this point?
Yes.
Like this distance from the wall, is that correct?
Yes. Yes. So basically, for the 1D bar situation, stress, strain, they're constant
Mhm.
for each section, right? And since strain is the first derivative of displacement, we know that the strain within each section should be linear change.
Okay.
So let's say FEA, everything is calculated at the displacement nodal displacement. So you calculate this one, calculate this one, these two are 0. And in between, you know it's linear change, you just use a straight line. And
Okay,
you're
so
done.
that's just the right assumption, that's linear between the.
It's not assumption, it's,
Right.
it's,
Exactly.
it should be, yeah, yeah. Yeah.
And then for number 2, I had a question, like, I wasn't sure if I set up the matrix correctly, so like I eliminate the boundary conditions, and then. And then I got the force direction, I wasn't sure about the sign though, like on the.
The external path force always follow the global XY coordinates. So if in the positive X is always positive, if in positive Y, it's
Okay,
always positive.
so I just was curious, like, so is this problem asking for the magnitude, or is it like the actual direction though?
It should include the direction. So is this the, what was the question asked? Like reaction force or something?
Yeah, it was the no, actually the applied load, because.
Oh,
most
apply load.
tests-
So it should, apply load is external path force, so you need to always include the correct sign.
Okay,
It follows the coordinates.
okay, follow.
Yes, yes, yes. You're welcome.